Aloha, this is Roger Brewer with the Hawaii Department of Health. This is a recording of a presentation I gave to the University of Hawaii April 1st, 2022, entitled TPH, or Total Petroleum Hydrocarbon, and the Assessment of Petroleum Risk. This presentation came about in part because of the need to have a more in-depth discussion about the chemistry and toxicity of petroleum compounds in jet fuel that were inadvertently drawn into the Navy's drinking water system in the fall of 2021. First, some terminology, some terms that I'll be using throughout the presentation if you're not familiar with them already. First is BTEX, possibly with MN attached. These are the individual compounds that are well studied: benzene, toluene, ethylbenzene, xylenes, plus or minus naphthalene and methyl naphthalenes. PAHs stand for polyaromatic hydrocarbons. The typical examples we deal with are naphthalene compounds like benzoate pyrene. TPH, Total Petroleum Hydrocarbon. This is everything else in the petroleum mixture with the non-specific hydrocarbons. This could be hundreds or thousands of compounds. Then a new term, HOPs, HOPs. And this stands for Hydrocarbon Oxidation Products. They're assumed to have the same toxicity as the parent compounds that were talked about. Now, at this point in time, these compounds are reported under TPH in analytical analysis by laboratories. Also hear the term action level. Sometimes I may say screening level, same thing. The concentration of a contaminant in a media at or below which no adverse health or other environmental impacts are anticipated. Just because you exceed an action level or a screening level doesn't mean necessarily there's a specific environmental problem. It just means that more attention needs to be carried out to evaluate if there is a problem or not. Also, you hear me talk about risk driver. This case, these are compounds in a mixture that pose the greatest risk to human health and the environment. So, for example, the concentration of these compounds in drinking water might still exceed an action level for that specific compound when action levels for all other components are met. First, I want to go over some petroleum risk misconceptions. First is that TPH is only useful as a qualitative screening tool. So TPH and hydrocarbon-related degradation compounds often dominate contamination. They must be quantitatively evaluated as part of environmental hazard evaluation, is the term we use, also referred to in some guidance as a risk assessment. Another fallacy often here is methods are not available to quantitatively assess risk posed by this TPH mixture of compounds in petroleum. Actually, the TPH risk can be quantitatively assessed in the same manner as individual chemicals like BTEX and pHs. And we've had methods to do this since the 1990s. I'll go over this in the presentation. Another misconception, TPH only needs to be considered if benzene and other individually targeted compounds are not detected. Well, this isn't necessarily true. The TPH component of petroleum in air, in soil, in drinking water can still pose a risk even when the concentration of BTEX and pHs and other compounds meet target risk or action screening levels. And then lastly, pre-approved TPH environmental action levels are not necessary. Let's just do a site-specific risk assessment for all petroleum release sites. In order to have an efficient assessment of hundreds of thousands of release sites across the U.S. alone, really requires some type of pre-approved action levels for soil, water, and air. This allows us to real quickly screen out low-risk sites or take care of releases that are easy to clean up and then focus on high-risk sites. So action levels, screening levels for TPH are really critical for environmental regulators and consultants alike. Quick references. First, for the Hawaii Department of Health, we have our risk-based TPH action screening levels, depending on which guidance you're looking at. It published in 2017 in the document Evaluation of Environmental Hazards at Sites with Contaminated Soil and Groundwater. We update this on a regular basis or every few years. Next update will probably be sometime this year, 2022. These are similar to the California EPA environmental screening levels, if you happen to be familiar with those. I helped develop the initial guidance there when I worked for California EPA. Another useful document to look at we've published is TPH risk case studies. It's in 2018. This talks about the collection and use of total petroleum hydrocarbon data for the risk-based evaluation of petroleum release sites. We worked with a group of consultants and oil company representatives and other entities with the ITRC group in 2016 to 2018 on a TPH risk document they published. And this is intended to represent an addendum or an amendment to that document. It's referenced in that document. It was published by our office. Other two reports we published related to petroleum. First, 2012, we did a field investigation of the chemistry and toxicity of TPH and petroleum vapors. And it was specifically with implications for petroleum for potential vapor intrusion risk. And we'll discuss this later on in the presentation. We published a paper on the results of the study and some of the implications in 2014. These references you can find on our webpage as you see below the slide. Also, we have recorded webinars on each one of these documents. Some other TPH references, I won't go through these in detail, but first you'll see 6 different entities that have published guidance from 1997 to as late as recently as 2016 on the toxicity of petroleum hydrocarbons in environmental media. And then in 2018, here's the ITRC document I mentioned, TPH risk evaluation at petroleum contaminated sites. Here's an outline of the presentation. So there was a really wide audience for this presentation I gave to University of Hawaii, anywhere from senior level environmental chemists, petroleum chemists with some oil companies, colleagues of mine joined in, I know, to students at the University of Hawaii where this is very new to them. So I really had to start off with the basics and cover a number of topics, but not get into too much detail on any specific topic. And that's what I'll do again today. So first we'll discuss environmental hazard evaluation or risk assessment, just some of the basics to set the stage for this. And then we'll talk about what petroleum is made of. Also, we'll talk about what specifically is TPH. What are these compounds? How can they be grouped and the toxicity and risk evaluated? And next, we'll very briefly go into how do individual TPH components partition when released to the environment. This starts to get into exposure pathways, inhalation, ingestion, or dermal contact with soil or water. Also, then we'll focus on what drives risk. Is it TPH or these HOPs, degradation products, or is it BTEX with naphthalene or some other pH at a site? This gets to the question, no BTEX, no risk, which often comes up. Then also, how are TPH and HOPs tested for? Just a quick discussion on that. And then I'll go over just a couple of questions that came up at the end of the presentation. First, let's talk about it. Environmental hazard evaluation basics, as we call it. These are some general types of environmental concerns posed by contaminated soil and groundwater that we try to assess at every site, or as needed, depending on the contaminant in the situation. So with contaminated soil, we almost always focus on direct exposure, specifically of children, especially of children playing in contaminated soil being exposed on a regular basis. Also adults over a longer term period. We might look at ecotoxicity, although it's not very common in most of the sites we work on. It's more site specific when needed. Vapor intrusion has been a big issue for quite a while now. So you have soil contaminated with solvents or petroleum fuels like diesel or gasoline. Vapors could intrude into buildings and contaminate indoor air. Fourth, an issue, contaminated soil, especially in places like Hawaii, where we have very restricted aquifers and drinking water resources, is leaching of contaminants out of soil and impacts on groundwater. And looking at contaminated groundwater, we often think about initially is contamination of drinking water wells. A big issue in Hawaii, a lot of coastal areas and areas along rivers and lakes and such, is discharge of contaminated groundwater into aquatic habitats. It may not be a source of drinking water, but it still could pose a risk to benthic organisms and other aquatic organisms. Then lastly is gross contamination concerns, where you have free product on groundwater or staining and heavy vapors and such coming from contaminated soil. Not necessarily a health risk issue, but could pose other problems. So as part of environmental hazard evaluation, you can assess risk or it can also develop environmental action levels. Again, this is also referred to as risk assessment. So some of the information needs include toxicity factors for individual compounds or mixtures of compounds. We'll talk about physiochemical constants to look at fate and transport, exposure assumptions, how much dirt does a young kid eat on average, or how much air do they breathe or water do they drink. Also just some soil and groundwater properties, permeability and such. And then we have separate models and approaches to assess risk or develop action levels for direct exposure concerns, or vapor intrusion concerns, leaching concerns, gross contamination concerns, and ecotoxicity. Here's an example. We take all these factors into consideration for benzene. So these are risk-based action levels published in our guidance in 2017 for all these different potential environmental concerns associated with benzene contamination. So you see 4 different media. We have soil and soil gas, vapors in soil, indoor air, groundwater. And with soil, we have, for all these media, we have human health related action levels, direct exposure, vapor intrusion, indoor air. You see action level for benzene indoor air. And the same thing in groundwater, different human health based action levels, one for drinking the water, they've had benzene in it, and for vapor intrusion. And you see action levels for gross contamination, taste and odors, smells and such. And then in green on the left is ecotoxicity. Again, for terrestrial ecotoxicity, it's typically site-specific. So we have action levels published for all these. And again, these are especially to screen out low-risk sites, or for just assist in rapid cleanup where a site-specific environmental hazard evaluation really isn't time and cost beneficial. You'll see with contaminated soil, we have these different environmental concerns. So if the action level for leaching is 0.30 milligrams per kilogram, it's lower than all the other action levels for direct exposure, vapor intrusion, gross contamination, and such. So we can also say that leaching drives the potential environmental concerns for benzene contaminated soil, at least initially, screening level. For groundwater, see the action levels for different environmental concerns. The action level for drinking water toxicity, 5 micrograms per liter, is lower than everything else. So we can say that drinking water toxicity drives environmental concerns for benzene contaminated groundwater. Again, just at initial screening level helps you highlight potential environmental concerns at a site, and then you do a more detailed evaluation of whether or not it's actually a concern there. This helps to ensure that we don't miss anything. Toxicity factors play an important role in assessing risk or developing risk-based action levels. Toxicologists will tell you that any chemical or anything is toxic above a certain dose per day. So in this table, you see different chemicals listed. Also a chronic toxicity factor is something a toxicologist would develop. This represents a maximum long-term safe dose for that specific chemical. And you see health effects if you exceed this dose over the long term, potentially posed by exposure to this chemical. So first, let's look at water. So water is actually toxic above a few gallons per day. This would be a short-term dose, actually, maximum short-term safe dose. Once you exceed this amount as an adult, you could develop a condition known as acute hyponatremia, which can be lethal. Aspirin is less toxic than water. It's a maximum long-term safe dose. You'll see on bottles of mini-tab aspirin in stores, it's typically 81 milligrams per day. And I always wonder why 81, why not 80 or 100 or 50? I'm sure there's a really detailed toxicological study where they derive this maximum long-term safe dose of 81 milligrams per day. So exceeding this could pose potential gastrointestinal problems. Now, barium is less toxic than aspirin. Maximum long-term safe dose, this is for a 15-kilogram child, about 3 milligrams per day. It's equal to about 2 1-millimeter grains, say sand-sized grains of barium per day, not expected to pose any long-term health effects. Once you start to exceed this, and there's a large safety factor, I'm sure, involved in these, you could develop multiple non-cancer related health effects. Arsenic is more toxic than barium. Maximum long-term safe dose for a 15 kilogram child, again, is 0.0045 milligrams per day. This is a tiny amount. This is equal to about 1 millimeter size grain of arsenic spread out over 2 years. It could pose, exceeding this value, again, a very large, at least order magnitude, I'm sure, safety factor built into this. Exceeding this long-term dose could pose potential multiple non-cancer related health effects. That's what a toxicologist does. I'm a risk assessor or geologist, not a toxicologist necessarily. I take what they do, and if you look at the example below, and it's just an example of how I or another risk assessor would develop risk-based screening levels. So in this case for silver, the maximum daily safe dose, according to toxicologist, about 75 micrograms per day for a 15 kilogram child. That's the average weight over 6 years. Then a risk assessor in a risk assessment would say, well, a child as a default drinks 0.78 liters per day. That's the EPA default. So 75 micrograms per day in 0.78 liters per day is equal to a concentration of silver in tap water of 96 micrograms per liter. So that's a risk-based action level for silver in tap water. Another term you hear toxicologists use quite often is dose makes the poison. So risk is equal to toxicity times dose, and dose is equal to the concentration of silver or any contaminant in whatever media you have times exposure. Say how many liters per day you're ingesting or how many cubic meters of air you're breathing or milligrams of soil or food. So in this case, you could have a high toxicity compound, say like arsenic, but very low dose. It would pose a low risk. But you could have another compound, say like barium, pretty low toxicity, but a high dose, high enough that the barium would pose a high risk. So just because arsenic, in theory, more toxic than barium doesn't mean that it always is going to drive risk or pose a greater risk if they have a mixture of barium and arsenic together. It depends on the dose of each that you're getting. This comes into play when we're thinking about what drives risk. Is it TPH in petroleum contaminated tap water or BTEX? We have a series of training webinars posted to our webpage. We did this in 2017. The first 5 parts of the training series deal with how to collect a good sample, a representative sample. And that's something the environment industry, including myself, I would say, did a poor job of early on. And in our office in Hawaii, I think we're pretty far ahead of most states now on how to collect representative samples. In part 6 of this series, once you finally get good sample data and good laboratory data, deals with environmental hazard evaluation if you want more details on this topic. The next in the outline, what is petroleum made of? Well, when laboratories test for petroleum, and they use something called a gas chromatograph, if you're not familiar with this, they typically have to run three different tests to assess the total concentration of TPH in a single sample. In this example, it might be a method 8015. Sorry, I've got the wrong number in the slide there. So for the really volatile compounds, the laboratory will run one test, and they refer to these often as gasoline range compounds, typically with 5 to 12 carbons in the compounds. BTEX would fall within this range, along with some other non-specific TPH compounds. Diesel range compounds, a little bit less volatile, so more carbons, C12, 12 carbons to 24 carbons. And the laboratory would report compounds, the concentration of compounds within this range as DRO, diesel range organics, versus GRO, gasoline range organics, or sometimes even TPH, gasoline, TPH, diesel. So they're testing this one sample in 3 different tests to give you 3 different ranges: gasoline range, diesel range, and then finally residual range. And these are really heavy hydrocarbon compounds, if there are any in the sample, like oil and tar and such. They're typically classified as greater than 24 carbons in the compound. In this case, it would be sometimes reported by the laboratory as residual range organics, RRO, or TPHO, something similar. So the laboratory, this has been a big problem that came up recently with contamination of groundwater around Red Hill, Navy's fuel supply, is that what you have to do when you get your laboratory data is you have to add up the concentration for each one of these ranges that they generate for a single sample. That's the total TPH. That's what you consider in a risk assessment or compare it to action levels. We'll talk about that later. Individually targeted compounds can be subtracted from the total concentration of TPH the laboratory would report, like BTEX, PHs. Here's an example, a gasoline fuel, a chromatogram for gasoline. So if you're not familiar with these, all these different spikes are different compounds in the gasoline that are being detected by the gas chromatographer. So that anything less than C12, again, we consider volatile. So most of the compounds in gasoline, you see all these peaks and things to the left of this C12 line are pretty volatile. So these are all the gasoline range organics. You see not much in gasoline in terms of diesel range organics. And this particular example here from the California Luft Guidance Manual, I think it's 2015, then the BTEX and naphthalene make up about 23% of the gasoline sample they use as a default. That can really vary sample to sample. But these TPH, all this other stuff, makes up about 77% of the fuel. So that's the question. What is all this other stuff? These are the other compounds in the fuel. How do we assess risk posed by that? This could be hundreds or even thousands of compounds. That's gasoline, so keep an eye on the chromatogram of that C12. Here's kerosene, JP5 fuel. This is the type of fuel, jet fuel, that was released from the Red Hill tank farm in the fall around Thanksgiving 2021. So here, the hump you see of all the peaks has shifted to the right, getting more centered around C12. So still within most of the compounds are within gasoline range organics or less than C12, but you're starting to pick up some heavier compounds, diesel range organics in the same fuel. So it's a pretty tight range of compounds here. One reason is for JP5 jet fuel, they use it on aircraft carriers. So you see all the highly volatile stuff is gone because the aircraft carriers don't want a lot of highly volatile and flammable fuel on board. But still, in this case, in a Department of Defense fuel specs for JP5 fuel, then they suggest there could be up to 10, 11% total BTEX, and methylene, naphthalenes, and such in the fuel. This really varies. Some of the more recent fuels that we're just now starting to get data on show very, very little BTEX. Most of it, again, is all this TPH, all these other compounds dominate the fuel. So when they dominate the fuel, even if maybe they're less toxic, but you have to start thinking about is the dose and exposure of the fuel high enough that it would actually drive risk. As kerosene, here's diesel, so now the hump has gotten really wide. It ranges from all the way down to a little bit of the highly volatile compounds, less than C8, to compounds over C16, which are going to be much less volatile. So diesel fuel, from a laboratory standpoint, it's a mixture of gasoline range compounds, organics, and diesel range organics. Very little BTEX in diesel fuel, and even naphthalene and methylnaphthalenes. It's a summary from the California Luft Manual again, about 99% TPH, all this other stuff, and only about 1% BTEX and naphthalene and methylnaphthalenes. That's just in general. It could be a little bit more, a little bit less, depending on the fuel formulation. So what is all this other stuff? This is it's the last project I worked on as a consultant when I was working in the mainland U.S. and other places. But this is a former gas station in the 1990s. They had dug out the tanks 10 or 20 years before this, and the developer was putting in an underground parking garage for a new development, new building going up on the site. And I was reviewing the risk assessments. I'm a geologist training background, academic, I also do risk assessment. I was actually reviewing the risk assessment for the site while we had an environmental consultant from our office out there just in case they ran into anything during the development. And you can see what happened. I call this the flaming pit. So this site actually passed a risk assessment at the state level but all they looked at was benzene, BTEX, maybe pHs. And so it passed. So that was the question. How can something pass a risk assessment and catch on fire? That red circle in the photograph, that's me sitting in the background asking myself this. So no BTEX equals no risk. And, we were definitely missing something in the 1990s. In this case, you could smell the gasoline vapors as you went out there, but so we'll mention in a minute, they were all the aliphatic compounds, non-specific aliphatic hydrocarbon compounds that were catching on fire whenever the backhoe bucket raked through this cobbly soil with quartz pebbles and such in it. So these aliphatic compounds, this TPH stuff, it's pretty obvious you wouldn't want these vapors getting inside this new building you're putting up on the site. They could have posed a vapor intrusion risk from a toxicity standpoint, as well as a fire risk. That's what, in general, what petroleum is made of, is all this TPH stuff and a little bit of BTEX and pHs maybe. So next, let's look at what is TPH, and how are toxicity and risk evaluated, and also how do these individual TPH components partition when released to the environment, because it starts to tell us something about exposure and risk. As I mentioned before, the groups have been looking at the toxicity of TPH, Total Petroleum Hydrocarbons, for a long time. One of the first groups put together was called the TPH Criteria Working Group in the mid to late 1990s. This is a group of people, experts from the oil companies, also within the Department of Defense, the Navy, the Army, the Air Force. It was actually led by a guy in the Air Force, and then several state regulators, including our toxicologist in Hawaii and myself when I was first getting started in this. They published guidance on how to assess the chemistry and toxicity of the TPH component of petroleum. And there were several other entities publishing guidance around the same time, and later Massachusetts, one of the first states to publish guidance on TPH in the early mid-90s. Then ATSDR, Washington, the Department of Energy, California EPA, then US EPA have all published reviews on how to assess the toxicity of the TPH component of petroleum. Pretty simple method, actually. And this, what they did develop was, first thing you do is you split up the compounds in the petroleum into aliphatic and aromatic carbon ranges. So aromatic carbon range just means the compound has a benzene ring. So in case we're talking about other compounds aside from benzene, since benzene is assessed separately, the aliphatic compounds, they're not anything that's not a benzene ring. So it could be like hexane, 6 carbons in a linked together in a chain. So the group, TPH Criteria Working Group, and these other entities, they developed various aromatic and aliphatic carbon ranges. And you see here in this graph, I have it simplified down to just 6. I think it's what Massachusetts used. So we have, you see EC, the E stands for equivalent. Sorry, it's a mistake in the slide here, equivalent carbon. I won't get into detail on how they calculate this. It's related to the boiling point, the molecular weight of the compound. We see the light range aromatics with 8 to 10 carbons or equivalent carbons, then mid-range or higher, 10 to 22 equivalent carbons. Aliphatic carbon range is divided into 4 different groups. And these are based on similar physiochemical constants like solubility and volatility, and also on toxicity. In aliphatics, there's 4 different groups were designated. So you have the light-in hydrocarbons, aliphatics with 5 to 8 carbons, 8 to 12, 12 to 18, and 18 to 36. So how these different groupings migrate in the environment and the toxicity will vary between the different groups. So TPH then now is the sum of these different aromatic and aliphatic carbon ranges. The number of carbon ranges can vary between guidance, but from a toxicity standpoint, you really just need, in this case, 4, maybe even less, or 6, maybe even less. So this group, the TPH Criteria Working Group in Massachusetts and other entities, then for each one of these different carbon ranges, they assign default molecular weights, vapor pressures, solubilities, Henry's constants, absorption coefficients, diffusion coefficients, and such. So once you start doing this, now we can start to treat these different mixtures, these different carbon ranges, in the same way we assess BTEX or individual compounds. They assign toxicity factors to each of the carbon ranges. And here, really, at least in terms of the way Massachusetts did it, they lumped everything into 4 different groups of carbon ranges in terms of toxicity. So you have the light-end aliphatics, C5 to C8, and then mid-range C8 to C18 aliphatics are more toxic than the lighter aliphatics. So the oil reference dose, the lower the number, the more toxic. You see here. Same thing with inhalation, reference concentration. The lower the number, the more toxic. C18 to C36 is the least toxic grouping of aliphatic compounds. And then only one grouping for aromatics. They assign one toxicity factor for all aromatic compounds with more than 8 carbons. In this case, the toxicity it's between the mid-range aliphatics and short-range aliphatics. So we have physiochemical constants, we have toxicity factors. Now we can actually assess risk and develop action levels for individual carbon ranges or for TPH in general. One thing you notice real quickly with respect to the physiochemical constants for each one of these groupings for the aliphatics and aromatics is that aliphatics prefer to be in vapors, in the vapor phase. So the Henry's constant is the concentration of the contaminant, the chemical in gas divided by the concentration in water. So when it's greater than 1, that means that most of these compounds will go into the gas phase, say if it's dissolved in water initially or discharged into water. Most of the aromatics, you see the Henry's constant is less than 1, so aromatics prefer to be in the water. So when you breathe something, say at a petroleum release site or even at a gas station, what you're breathing in mostly is the aliphatic compounds. And when you have water contaminated with petroleum, then most of the compounds in the water are going to be aromatics because they're more soluble and also they're a lot less volatile. So now we're getting somewhere. Here's the TPH carbon range composition versus exposure pathway. So we'll start to merge this with risk assessment. And one note here is the carbon range makeup can vary with respect to the fuel formulation, but this gives you a general idea of what's going on. So again, for say if you release gasoline, kerosene, or diesel to soil, then what happens to the compounds? When the vapors in the air above that release, it's going to be mostly TPH, and most of the TPH is going to be these aliphatic compounds, the light range and mid-range aliphatic compounds. The blue represents BTEX. You'll get some BTEX in the vapors also when you release it to soil. This is actually from field data that we collected at a site for vapors associated with contaminated soil. Kerosene, the same way. Most of the vapors are going to be TPH aliphatic compounds, and same thing for diesel, varying amounts of BTEX depending on the formulation. For contaminated soil, you see in the middle, this is the TPH versus BTEX makeup of the fuel itself. So you see for gasoline, there's a large pie wedge of blue, that's the BTEX. For kerosene, then that wedge gets much smaller, and depending on the formulation, it could be maybe up to 10% BTEX, but most current formulations is a lot less than that. And when you look at diesel, it is much less, almost no BTEX in the diesel. It's almost all TPH again, as we mentioned before. Now, if you look at the water associated with this, say if you put gasoline or kerosene or diesel on water, then again for gasoline, most of what's going to be in the water is going to be the aromatics, especially the BTEX, more soluble, less volatile. And you also get some TPH, but it's going to be other aromatics. For kerosene, same thing, depending on the formulation, the TPH is going to be made up of all the aromatics, and that's going to dominate what's in the water dissolved into it. Again, the amount of BTEX depends on the formulation, and the same thing for diesel. So that's in general how things break up between TPH and BTEX. Now we can start to look at the specific carbon range makeup of TPH in fuel and in water and the vapors. And again, as I mentioned before, for the fuel samples, these examples here are based on the California Luft Guidance published in 2015, where they have default carbon range makeup of the different fuels. So for gasoline, you see a lot of green in the middle column here for fuel. And those are the C5 C8 aliphatics. So most of gasoline is made up of C5 C8 aliphatic compounds. A little bit of heavier aliphatic compounds, greater than C8 to C18, and some greater than C8 aromatic compounds. That's what's in the fuel that we can measure. You see with kerosene in the fuel, it's going to be mostly yellow in this case. So all the light range stuff is disappearing. It's made up more of the mid-range aliphatic compounds. and then varying amounts of lighter range aliphatics, and then C8 and higher aromatic compounds. And then when you get to diesel, at least according to the California Left Manual, you shouldn't see any C5, C8 aliphatic compounds in diesel. We'll think about that again in a minute. So that's in the fuel phase. Now in the vapor phase, again above gasoline, if you test the vapors above gasoline, fresh gasoline especially, it's going to be all C5, C8 aliphatics. And for kerosene, you'll start picking up more of the heavier aliphatics because that's what's in the kerosene fuel. And in diesel fuel, or diesel, depending on the site, it can really vary, but it can be dominated by these longer chain aliphatic compounds, which are also, if you recall from an earlier slide, they're more toxic. So that's interesting just from a TPH standpoint. C5, C8 aliphatic compounds are the least toxic. C8 to 18 aliphatic compounds are the most toxic. So in terms of TPH, diesel vapors are more toxic. It poses the greatest potential risk than gasoline vapors. And we measure this in the field. So now we have a good idea of the carbon range makeup of TPH. In the fuel, we know what's in the vapors. Ideally, for the vapors, again, we did detailed field study where we collected soil vapor samples at lots of sites in Hawaii and vapor samples over fresh fuels. That's the best way to do it. We wanted to try the same thing with dissolved. So what's the carbon range makeup of dissolved TPH compounds in water that's in direct contact with fresh fuel? We tried to do that. So we ran a series of laboratory studies, 2019, 2021, where we got lots of flasks. A laboratory did this for us. They put a layer of fresh fuel on water in the flask, either gasoline, diesel, JP5, JP8, jet fuels, let it equilibrate for 20 days, and then tested the water under the fuel for BTEX pH, H's, and especially the carbon range. What's the aliphatic and aromatic carbon range make up of dissolved phase hydrocarbons? We were really interested in that because once we get that, we can start looking at the risk posed by TPH related compounds. And we could even calculate weighted toxicity factors, we'll talk about in a minute. And this we were going to use this to update our TPH toxicity-based action levels for drinking water in our guidance. Well, in the labs, they tried, but none of the 3 labs that tried to do this could accurately, reliably separate aliphatic and aromatic compounds in the water. So in the end, it didn't work. We learned a lot, but trying to measure this in the laboratory didn't work. So instead, what we had to do is model this. So if we know the concentration, if we know the carbon range makeup in the fuel, and we know the fuel is in contact with water, we can actually model the effective solubility of the individual carbon ranges, and then get an idea of the makeup of dissolved phase TPH in water in contact with fresh fuel. So you see that here in these pie graphs. So for gasoline, we can predict based on the makeup of gasoline that in the dissolved phase in water in contact with gasoline, most of the compounds, again, are going to be made up of C5, C8 aliphatics in terms of just the TPH component. And then all the rest of it is going to be these other aromatic compounds. So the aliphatic compounds, they like to be in air, but there's so much of it in gasoline, and they're so soluble, you're still going to see quite a bit going into the water phase. And the rest is going to be made up of these sort of water-loving aromatic compounds greater than C8. Again, if you recall from the earlier slide, a lot of what dissolves in the water also for gasoline is the BTEX component. In this case, we're just looking at the chemistry of the TPH makeup. Kerosene and diesel fuel alike, most of the compounds, again, that we can predict based on simple models, it's really pretty simple chemistry, that most of what's going to be dissolved in the water are these greater than C8 aromatic compounds. So that starts to give us an idea of the toxicity of the mixture of TPH mixture of dissolved phase hydrocarbons in water, unrelated to BTEX. So now we have physiochemical constants, we have toxicity factors for these individual carbon ranges. You'd think, well, the next process would be, we'll just forget about TPH, let's just develop action levels for individual carbon ranges, say for these 6 different carbon ranges. We broke it into the same way we did for benzene. You know, it's possible to do that, but it's not practical for several reasons. One is just, it's not necessarily cost beneficial to do this. It's going to take more time by laboratory, cost a lot more money. And also the There are very few labs that can do this type of carbon range quantification or analysis. And also, especially with respect to hydrocarbons in water, they're going to start to degrade pretty quickly. So you get these degraded mixtures, degraded compounds that the carbon range analyses aren't going to pick up. So that was a problem. So instead of developing risk-based action levels for carbon ranges, a much more efficient, practical approach is to think about what the weighted toxicity of all these carbon ranges are within a mixture, and then develop a TPH, risk-based action levels for TPH based on the weighted toxicity of the mixture. So one way I like to think about this is you can do the same thing with cookies. So say you have chocolate chip cookies, and you're wondering how many calories in a single chocolate chip cookie. Well, if you know the individual ingredients and you know the calories in each ingredient, you can test the cookie for each individual ingredient. So you know the concentration of chocolate chips, the concentration of flour and butter and everything else. And then you can calculate, based on that, from the individual compounds, you can calculate what the total calories are for that cookie. But a much easier way to do it, if you know the proportion up front of chocolate chips and flour and everything else in the cookie, you know the calories associated with each one, then you can calculate a weighted calorie content for that cookie, or a weighted toxicity if you want to think about it. So you can do that up front. You don't have to test for every individual compound, every individual ingredient in that mixture. And it's also will set there's a very tight range or specific range of how many calories a chocolate chip cookie can have. If it was pure chocolate, let's say it has the highest number of calories, well, that's the most calories a chocolate chip cookie can have, is the number of calories in pure chocolate, if that was the only ingredient. The lowest number of calories it could have is the calories for, say, for flour. Think of that as the least toxic. There's nothing in the cookie but flour. And you know the calories per flour, that's your lowest caloric range you could have. Well, you can do the same thing for mixtures of anything. In this case, say mixtures of BTEX and the carbon range compounds in mixtures in dissolved phase in water. So in this case, you could test for individual compounds, BTEX, and you could test for individual carbon ranges. Say hypothetically you could, and then average those together, come up with a weighted concentration. A much easier way to do it, if you already know the general makeup, is just to calculate a weighted toxicity of the aliphatic compounds, the aromatic compounds. So we do this by, if you see on the bottom, weighted toxicity, in this case we use a harmonic mean approach, is 1 divided by the percent fraction of ingredient A, say it's a C5-C8 aliphatics, divided by the toxicity of that compound or that group, plus the fraction of B divided by the toxicity of that and such. And this will give us the weighted toxicity or a TPH mixture. Again, do the same thing for cookies. So if you want to get into more detail on this, we discussed the calculation of weighted toxicities in our guidance document in 2017, evaluation of environmental hazards at sites of contaminated soil and groundwater. It's in Appendix 1. Also, in the memorandum we published in 2022 of this year, specific to recommended risk-based drinking water action levels for its dissolved phase TPH associated with JP5 jet fuel. We go into a lot more detail on calculation of weighted toxicity factors for mixtures of TPH groups, compounds in that document. So we can do this. We can, once we know the carbon range makeup of these mixtures, whether it's in air, in fuel, or dissolved in water, then we can calculate weighted toxicity factors for the different exposure pathways, inhalation, dermal contact, and ingestion. And we can use these weighted toxicity factors then to calculate a single action level for the TPH group in each one of these different phases. So in this case, you see the weighted toxicity factor for gasoline vapors based on the mixture of C5, C8 aliphatics and 18 aliphatics and greater than C8 aromatics. The reference concentration calculated for that mixture is 281 micrograms per cubic meter. So once we have that, we can calculate a risk-based screening level for air. You see the similar reference concentrations for kerosene and diesel. The reference concentration you see is getting lower as you go toward diesel. This is because you're incorporating more C8 to C18 aliphatics in the air in that mixture, and they're more toxic than C5 C8 aliphatics. So you're incorporating more toxic compounds in the mixture. Reference concentration goes down, and if I'd shown you an air concentration for the mixture, it would also be going down. We'll look at that in a minute. In diesel especially, at least in some cases, the reference concentration could be pretty low because there's so much of the mid-range aliphatics. You see the similar mixtures and calculated weighted reference doses for the fuel. I don't show the dermal reference doses in there. We can also do those. Again, for TPH in gasoline, reference dose 0.025 milligrams per day. For kerosene, we're starting to incorporate more of these mid-range, the yellow aliphatics. It's going to be more toxic, so the reference dose is going down. It's about the same actually as for diesel in fuel, a lower reference dose. So TPH component of kerosene and diesel are more toxic than gasoline. Again, you'd be assessing BTEX separately. Then dissolved phased TPH mixtures associated with 3 different fuel types. You see the reference dose. In this case, I included the dermal reference doses for dermal contact and reference concentrations. And again, they go down as you go from gasoline to kerosene to diesel, but because you're incorporating more of the mid-range aliphatics and these other gray aromatic compounds. So we have weighted toxicity factors now for these carbon range mixtures associated with TPH, each one of these fuels. Now we can calculate TPH-based action levels for air, soil, looking at fuel, and dissolved in water. Here's an example, current example from 2017, our action levels. These are the action levels for TPH associated with middle distillate fuels. And again, this is the total TPH from all these 3 different ranges you add together. So you see different action levels for diesel fuel in soil, 220 for direct exposure, 130 micrograms per cubic meter in vapors or for indoor air. And then you see all the other action levels for leaching and such. For drinking water, our middle distillate action level, we have it for drinking water right now is 400 micrograms per liter of TPH associated, say, with diesel fuel and water. One issue with this action level, which we've pointed out before, is it assumes it's heavily degraded, not volatile. So if it's volatile, so we assume there's no inhalation exposure. We're updating our action levels now to take into account inhalation exposure and a better understanding of the carbon range makeup. That should be done later this year. So it's going to be lower, probably closer to 200. So we can do the same thing for gasolines. We're working on it now, and even residual fuels, the heavier fuels. And again, we plan to update these sometime this year. So then let's look, now we have toxicity factors for these TPH mixtures, and we can do the same thing for HOPs, the mixtures of TPH and BTEX that are degraded. Let's think about what drives risk at a site. First, let's look at soil. So here, let's assume for TPH in soil, that the carbon range weighted action level, compare that to what, say, for benzene in soil, thinking about what's going to drive risk. So the soil action level for benzene is 0.3 milligrams per kilogram. So say you go out to a site, you collect a sample, test for benzene, you compare your data to this action level, 0.30 milligrams per kilogram. If it's less than that, you're done. For gasoline, this carbon range weighted TPH action level for gasoline that we use now is 100 micrograms per liter. For diesel, it's 220. Residual fuels, it's 500. These are based on different concerns. It could be gross contamination or leaching or whatever, or direct exposure. So the question here in terms of what drives risk is, could this TPH action level still be exceeded even though benzene in the soil is less than 0.3 milligrams per kilogram? Well, looking at gasoline, that could be the case because at least in older formulations of gasoline is still a fair amount, there's a lot of benzene. Even in the newer formulations, there's still some benzene. So let's say if you just tested the soil for benzene and then cleaned up the site based on benzene, that might actually work for gasoline contaminated sites, especially if it's pretty fresh fuel release. But only really if you use a 10⁻⁶ risk, 1 in a million risk, that's when the action level for benzene in soil is 0.3. Sorry, I've got the wrong numbers underneath this slide here. If you use a 10 to the minus fifth risk level for benzene, then your action level for benzene is actually going to go up because you're not being as conservative. So benzene may not drive risk anymore. TPH may be the main concern at the site. And for kerosene and diesel, there's very little benzene or BTEX in the fuels to begin with. So TPH most likely is going to drive risk and drive cleanup needs for releases of kerosene and diesel, not BTEX. So definitely no BTEX, no naphthalene, whatever, doesn't mean no risk at kerosene and diesel sites. And it may not at gasoline sites. And again, underneath here, you see these footnotes. I've got the wrong numbers in there. I just noticed there. That's actually benzene action levels in air, not in soil. So that's the point. TPH can drive risk for cleanup of contaminated soil. Again, this is because dose makes the poisons. There may be a little bit of benzene in the soil, so high toxicity, but very low dose, low concentration in the soil. So the risk overall would be low in comparison to TPH, this mixture of other aliphatic aromatic compounds. The toxicity overall may be much lower than benzene. The screening levels may be 100 times higher or more, but because it dominates the contamination in the soil, the dose is going to be much higher, so that it would pose high risk, and TPH would be the risk driver, not BTEX or benzene. We see the same thing for carbon range weighted TPH action levels for air. This is in our guidance also. So for say indoor air, ambient air, our benzene action level is 0.36 micrograms per cubic meter. That's based on a 10 to the minus 6 target cancer risk, 1 to million cancer risk. And look at the concentrations, the action levels for TPH as gasoline, kerosene, and diesel. Again, based on this carbon range weighted approach, they're at more than 100 times higher, almost 1,000 times higher, 290, 230, 130 micrograms per cubic meter. So you may think initially, well, benzene is our main concern because look how low the action level is. But again, there's very little benzene in kerosene and diesel, so chances are it may not be driving risk. Maybe the TPH is more of a concern. And that's exactly what we see at sites. So we actually collected vapor samples over fresh samples, vapor samples over fresh samples of gasoline, diesel, and JP8 that we had. And for fresh fuels, not a big surprise. There's a lot of benzene in the vapors associated with gasoline. And if you use a 10 to the minus 6 screening level or action level for benzene, 0.36 micrograms per meter, cubic meter, then yeah, benzene is going to drive risk posed by vapors from fresh gasoline. We were surprised. We saw a lot of benzene in the vapors from diesel and JP8, which it's not supposed to be in there, or not, maybe just traces, but there was a lot in the vapor samples. It actually suggested benzene would drive inhalation risk from vapors from diesel and JP8. That was a big surprise. It really depends on the formulation, who's making the diesel, who's making the JP8. And again, if we used a 10 to the minus 5th target cancer risk for benzene, now the action level is 3.6 micrograms per cubic meter. In this case, all the aliphatics in the vapors are going to drive risk over benzene. So the TPH would drive risk in that case. But we went out to actual sites in Hawaii and collected vapor samples, from subsurface soil gas, and tested them. We saw hardly any BTEX in the samples. And even in US EPA's, they have a gasoline release site vapor database. Look at all their data for vapor samples around gasoline release sites. Hardly any BTEX in the vapors, even for gasoline. And so we saw that in gas stations here also. So in that case, in reality, at least for aged releases, the TPH, all these aliphatics drive risk, not BTEX for vapor intrusion concerns, even at a lot of the gasoline sites, say at least a third of them. And then we look at JP8 release sites and diesel release sites, and sure enough, there's no BTEX. We don't see any of that in the vapors. What we think is happening at the gasoline sites is that the aromatics, they don't like to be in the vapor phase. So if there's any moisture in the soil, as the vapors are coming off the fuel underground, the aromatics, including the BTEX, are going to diffuse into the moisture, get sort of scrubbed from the vapors. That's why we don't see benzene and a lot of gasoline release sites in particular, and why TPH actually drives vapor intrusion risk at these sites, not BTEX. And now, so that was a TPH in soil, TPH in air. So next, here's some example carbon range weighted TPH action levels for tap water. This is something we're working on now to update these. Again, these are for fresh, volatile plumes of fuel in water. So the benzene screening level for tap water is it's the US EPA MCL 5 micrograms per liter. And again, the TPH components, remember what dissolves into the water. It's for gasoline. There's still a lot of C5, C8 aliphatics possibly, but especially a lot of these heavier aromatics, greater than C8 aromatic compounds, a lot less toxic molecule for molecule than benzene. You'll see the action levels can easily be 10, even up to 100 times higher than benzene. So again, you might mistakenly, I would say, think that benzene drives risk for petroleum contaminated tap water or groundwater, just because the action level is so high. And you'll see for the TPH action level for gasoline, kerosene, diesel, it's going down. It's lower for diesel compared to gasoline because in diesel, you have a lot more dissolved, these mid-range aliphatics in the water that are more toxic than the lighter range aliphatic compounds. These are, for example, only these action levels. We're still working on these in-house. And especially for something like kerosene fuel, the action level assumes there's a lot of xylenes in the fuel to begin with, and that's getting in a mixture. Actually, that's for degraded compounds. It assumes there's could be some C5, C8 aliphatics in the mixtures and such. So we're looking at more recent formulations of fuel, and we'll update these numbers based on that, the more reliable carbon range mixtures. So these are all draft just ideas to start with. Now we look at think about risk. What's driving risk for releases of fresh fuel into groundwater? It's the source of drinking water. Well, for gasoline, it probably is going to be BTEX, because there's a lot of BTEX in gasoline. That's going to dominate what's in the groundwater. You'll still get some C5, C8 aliphatics mixed in, but chances are your BTEX can drive risk because it still makes up a huge portion of what's dissolved in the water. For kerosene and diesel, it depends on the formulation. Older formulations of kerosene and apparently even diesel, since we see a lot of benzene in the air, could have had decent amounts of BTEX, especially naphthalene in them. And BTEX could drive risk for fresh releases of these fuels in groundwater. But when we look at actual site data, we don't see much, especially for recent fuels, because there's just very little BTEX in the fuels themselves. And most of what's in the groundwater are these non-specific C8 and higher aliphatics. So for fresh releases for current fuels, TPH is really going to drive risk because there's not much BTEX in the fuels to begin with. So that's the fresh fuels. So for gasolines, sometimes BTEX, benzene in particular, is going to drive risk over TPH depending on your target risk that you use. Apply to gasoline and the formulation of it. For kerosene, it's like JP5 and diesel fuels, TPH is going to drive risk in most cases for what's going into the air, inhalation risk, and what's in the soil from a direct exposure risk. So next I want to look at the water again. But in this case, let's think about the weighted toxicity of not just the TPH, but the BTEX in the water. So let's say we know that what dissolves in the water is a mixture of BTEX aromatics and TPH related aromatics. What if all these compounds degraded? So now we have a mixture of degraded compounds. And let's think more about the toxicity, weighted toxicity of those mixtures. So we will calculate weighted toxicity in the same way we did for others, for individual carbon ranges. We just look at the TPH and BTEX makeup, the percentage of each one of these components, and the toxicity factor associated with each component, and we can calculate a weighted toxicity for a degraded combined TPH and BTEX mixtures. This is a slide to summarize that. So let's say in the water now we have a mixture of TPH and BTEX. We know the percent makeup of each one and the toxicity factors for each one. We degrade them into this mixture. So at least as a starting point, we assume that the toxicity of the mixture is the same as the weighted toxicity of this. If the degraded mixture is the same as the weighted toxicity of the undegraded mixture as a whole. And we're not going to get into this in detail, but these hydrocarbon oxidation products, these HOPs, as the Californians call them, they're made up of polar acids and esters, alcohols and ketones and phenols and such. So as a default, we assume again that the toxicity of this mixture is the same as the toxicity of the weighted toxicity of the original hydrocarbons. And the laboratories can report this as TPH, not as HOPs. And one thing with water samples is you don't want the laboratory to run the water through silica gel, which is used to take out all the polar compounds, because all these degradation products can be polar. What we want is the concentration of these degradation compounds in the water. We need better test methods both for TPH and for testing the degradation products. We can get into a lot of debates about what the original mixture was of the compounds with the hydrocarbons, depending on the fuel formulation, and what's the toxicity of the individual of the mixture, the degraded compounds. But I like this quote from Aristotle as far as how much precision we need in this discussion is the mark of an instructed mind to rest easily with the level of precision that the decision requires, and not to try an exactness that is unnecessary for the problem. So we can come up with a pretty good estimate of what the weighted toxicity of the HOPs degradation mixtures is, and develop action levels for that, at least as a screening point. And that's going to be adequate for most sites we deal with. In some cases, you may want to get more detailed data, the original fuel formulation and such, but in most cases you don't need to. So here's some example carbon range plus BTEX weighted HOPs action levels, for degraded plumes. And you can see here's our BTEX, our benzene action level again is still at 5 micrograms per liter, just as a reference, because now we're assuming the benzene and other things are all degraded and mixed in with the TPH the lab's reporting. If you look at the TPH action level now for degraded gasoline mixtures, it's gone from 300 something down to 190. This is because we're including degraded benzene in this mixture and this TPH reported by the laboratory. You'll see the action levels for kerosene fuels and diesel fuels for the degraded mixtures actually go up a little bit. And that's because we're assuming now that these mixtures, the TPH now includes less toxic xylenes. So the weighted toxicity of the degraded mixture is it's not as toxic as the weighted toxicity of the original carbon range mixture. This assumes, especially for kerosene, you see it went way up, almost doubled. That's based on the carbon range and BTEX mixture of JP5 jet fuel that was in some older 1990s era military specs for JP5 fuel. Some of the newer fuels we're finding now, including what's stored at Red Hill at this point, have very little xylenes in it. So if we were going to calculate an updated TPH action level, say for JP5, it would go down some because we're not diluting this mixture with less toxic xylenes. This is just for example only. So what's the risk driver then for petroleum contaminated tap water, TPH or BTEX? For fresh releases, for gasoline, again, even if it's for the fresh releases, we already went over this. Benzene might drive risk, probably would be for fresh releases of gasoline. It's not degraded yet. Probably not for kerosene and diesel for new formulations. For degraded mixtures, well, of course, now all the BTEX is degraded. So TPH, or these HOPs compounds, which are reported as TPH, are all going to drive risk. So for degraded plumes, TPH and HOPs are especially important, including for gasoline. So that's the point, is that TPH and or HOPs almost always drive risk for middle distillate releases and can for gasoline releases, even for fresh gasoline releases if you use less than 10 to the minus fifth cancer risk. The whole point of all these discussions is TPH is important. We have ways to quantify it. How are TPH and HOPs tested for? Last slide, really. I'm not going to say much about this other than we discussed how current laboratory approaches give you 3 different concentrations when they test for TPH in a sample: gasoline range, diesel range, residual range. This works for laboratory, but from a risk standpoint, it's confusing. We really just need we need one number from the laboratory. What's the total concentration of TPH in the sample? And for water samples in particular, we don't want them to run it through silica gel. We want to include all these degraded compounds. So give us one number, and what you would do as a consultant and regulator is you have to add each of these ranges together to get a total TPH concentration. And that you compare that total TPH concentration to the action level specific to the fuel that was released, either gasolines, middle distillates, residual fuels. So you can get site-specific carbon range data and develop action levels. They're actually very useful if you're looking at a TPH in soil gas and indoor air, because that can really vary from site to site, from fuel to fuel, based on the same fuel, different formulations. But otherwise, it's not really cost beneficial or that useful to get site-specific carbon range data unless you have a very rare release of fresh petroleum fuel like we did at Red Hill with the Navy's drinking water supply into a drinking water system. In that case, it would be important to get fuel-specific carbon range data. We do a much better estimate of what actually dissolved into the water and went through the drinking water system to assess risk. And we're working on that now. Again, we need better test methods for both TPH and total HOPs. So in summary then, no BTEX doesn't mean no risk, and their methods are available to assess risk posed by TPH compounds. TPH always needs to be considered at any petroleum release site, even if benzene and other individually targeted compounds are detected. And you'd be surprised, I think some people will, from a standpoint of risk, the TPH is more important than benzene and other pHs. Also, TPH-related compounds often drive risk at petroleum release sites we just mentioned. So they can still pose a risk even though the concentrations of BTEX and pHs, they're detected, but they're below action levels. TPH compounds still could pose a risk. We need better test methods for both TPH and HOPs. And carbon range data and site-specific action levels, they're primarily useful for testing of parent fuels associated with large fresh releases, again like we had here, and also for testing of indoor air and soil gas associated with middle distillate fuels in particular, looking at vapor intrusion concerns or indoor air exposure concerns. And site-specific action levels for TPH and even use of carbon range data, it's allowable, but they're going to fall within some narrow range of possibilities. And they'll rarely be needed again. So that was the end of the presentation. And there was general comments and questions about petroleum formulations, especially say with diesel fuels and such. It can vary quite a bit. That's why we see different amounts of aliphatics and even BTEX and vapors from diesel fuel releases. You also have to think about degradation. But the questions in general were pretty basic, and I covered most of them in this recording of the original presentation. Just added in some notes. This whole issue of do you need to test for TPH or not, it's surprising to me. It's been going on for almost 30 years now, 25 years, and it still comes up. We still hear no BTEX, no risk. If you have detectable BTEX, you can ignore TPH. Well, that's not true. We know now for the reasons I've discussed here. And that's some of the interesting part of science. This quote by Neil deGrasse Tyson here, there are problems yet to be identified, like TPH, because they only show up after we've learned to even ask such questions and think about it in more detail. That is what keeps this fun. Now, two of the questions that came up, some quick notes on that. There was a discussion about site-specific studies. And again, a lot of this relates to what happened at Red Hill. If you're not familiar with that, just Google it. Look for it on the internet. The release of 30,000 gallons of JP5 jet fuel got into the Navy's drinking water system around Thanksgiving 2021, contaminated the whole system. So if at the time, we didn't have very good data, carbon range data for what the actual makeup of the fuel, which we really need to estimate and model what the carbon range makeup, the dissolved phase TPH would be in the water, and to assess the target weighted toxicity. So if you're going to do a site-specific study, then really just for a fuel and for the soil, but to model what goes into the water, it's important to get a sample of the fuel and then test for a really broad range of carbon range compounds. So you can see here a lot more than 6. They're more like say 11 or 12 different ranges. And each one of these ranges has different solubilities and such. So you need a broad breakdown like this to estimate exactly what gets into the dissolves into the water, concentrations and percentages and such. When you're looking at site-specific evaluations of the toxicity, say of fresh contamination in water anyway, you don't need such a breakdown of the aliphatics and aromatics. We're mainly focusing on toxicity. Won't be that useful in general. In most cases, maybe except in the recent Navy instance, most of what gets into a well is going to be degraded, so you're not going to see any much BTEX or carbon range, individual carbon ranges in the water sample anyway. You just have a bunch of polar degraded stuff. For vapors, site-specific study, that can be really useful, especially at middle distillate sites. It's important to get some carbon range data for soil vapor samples or indoor air samples. But in this case, you only need for laboratory to break it down into 3 different carbon ranges. There's 3 different toxicity factors or toxicity-based groupings of these compounds in the aliphatics, 2 for aliphatics and 1 for aromatics. So a lot of labs can do this now. Very few labs can give you a detailed breakdown like I have listed under fuel and soil. So we talked about that. And again, we got fuel, JP5 jet fuel from the Red Hill tank farm. We're getting detailed carbon range analysis done on it so we can get a better idea of what the total mixture, the weighted toxicity of the mixture was that dissolved into the water. It's still in the groundwater. There's some different references for petroleum HOPs. Again, that's the next question that came up, is the toxicity and the chemistry of degraded petroleum mixtures dissolved in water. So a very useful paper to look at is Zemo et al. In 2016, Life Cycle of Petroleum Biodegradation, Metabolite Plumes, Implications for Risk Management at Fuel Release Sites. Look at that in more detail in a minute. And then we summarize and review this document, expand on it in our 2018 document for TPH case studies, collection and use of total petroleum hydrocarbon data for the risk-based evaluation of petroleum releases. Attachment 5, we go into detail. Just a few quick notes on this. We already have a posted recorded webinar on this topic. It's a 2017 webinar. Just look for it on the webinar webpage you see here, TPH Risk Case Studies, Part 2. We looked at metabolite tap water toxicity and associated with a hypothetical gasoline release at a gas station. Just to summarize this, then again, we discussed this some. You can use a similar weighted mixture toxicity approach, at least in theory, can it be applied to TPH-related metabolites in drinking water. So to do this, if you're just looking at degradation compounds, so you want more site-specific study of degraded petroleum, the first step would be to designate metabolite families similar to carbon range groupings and assign toxicity factors to each of these metabolite families. Step 2 would be to estimate the metabolite family makeup of degraded TPH in the water at the site. And it could vary depending on the state of degradation. Step 3, once we know what the makeup is, we know what the toxicity of individual components are, is to calculate metabolite suite weighted toxicity factors. And we can use that to calculate metabolite suite weighted screening levels. So step 1, this is Zemo et al. In 2016 already did this. They looked at the types of metabolites associated with degraded, in this case diesel fuel, at a site, and they grouped it into 5 different metabolite families: alcohols, esters, ketones, aldehydes, and phenols. They looked at compounds associated with each type of metabolite family, and they gave it a toxicity ranking: low toxicity, low to moderate, or low moderate and such. And then they gave an estimated range, in this case just of an ingestion reference dose for each one of these metabolite families. So the lower the number, these last 2 columns here, the more toxic it is. So the alcohols, they estimate a range for the toxicity factor associated with ingestion, the oral toxicity, of 0.1 to 1.0, the reference dose. Where then you look at phenols, the most toxic, they were estimated a range of reference doses for phenols of 0.001 to 1.0. So There's step one. We know toxicity factors. We have metabolite families categorized. We have toxicity factors assigned to each metabolite family. And again, here they're assuming these degraded compounds aren't significantly volatile, so mostly focusing on ingestion and also dermal exposure route. Here we're just focusing on ingestion in the example. Step two then would be that they designated degradation stages versus the metabolite family makeup. So right in the source area, they designated 4 different degradation stages, stage 1, 2, 3, and 4. So stage 1 in the source area, you still have some dissolved phase hydrocarbons, but you're starting to get a lot of breakdown of some of the metabolites. Stage 2, and sort of a smear zone. Now in this zone, all the hydrocarbons are soon to be degraded, and you only have these metabolite groups. Stage 3 is sort of an average of stage 2 and stage 4, but stage 4, you're getting more and more degradation, different metabolites as you go further away from the plume. So you have 4 different degradation stages. Each one of these degradation stages, then they predicted a mix of these individual metabolite families. So now we have a mix of the metabolite families. We have a toxicity factor assigned with each mix, stage 1, 2, 3, and 4. So now we can calculate a weighted toxicity factor for each mixture. So we can calculate a weighted toxicity factor for degraded, it's the TPH plus BTEXN components in the source area, all the way to stage 4 is away from the source area, or just older stage of degradation. This is all again discussed in the presentation I discussed before. It's already posted to our webpage. So with each one of these, that's what Zemo et al. Did in 2016. We took this one step further. We say, well, if you already have the metabolite mixtures for each one of these degradation stages, and you have toxicity factors associated with each one of these metabolite families, you can calculate a weighted oral toxicity factor for each one of these stages. And then you can use that to calculate screening levels. So that's what we did in our 2018 document. So for stage 1, based on their mixture of these metabolite families, we calculated a weighted oral reference dose range from a low of 0.02 to a high of 0.2, depending on the range of toxicity factors they proposed for those specific metabolite families. For stage 2, you see the toxicity factor is a little bit lower, 0.04, so it's increasing number, decreasing toxicity. Stage 3 goes to 0.05, stage 4 to 0.07. Not a big difference, but their point in their paper, and we also concluded in our review, at least based on their toxicity factors, is that as these plumes degrade more and more, they become less and less toxic. So the toxicity factor on average will decrease by a factor of 4, actually become less toxic by about a factor of 4. So these were the metabolite suite weighted toxicity factors. If you look at the most conservative ones they have. Now compare this to the toxicity factors we estimated for our HOPs mixtures. The dissolved phase carbon range plus BTEX mixtures from our fuels I discussed earlier. And they're not that different. For gasoline, we estimate a weighted toxicity factor for HOPs mixture of 0.035. For kerosene, a bit more toxic, 0.030. Diesel, a bit more toxic, 0.029. So the toxicity factors is very similar to what Zemo et al. Estimated or predicted, or it could be extracted from their paper in 2016. So they're at least using their most conservative toxicity factors. They're also saying the same thing we concluded, is that the degraded hydrocarbon mixtures have a very similar toxicity to the toxicity of the weighted hydrocarbon mixture for the parent compounds. So that was it. There's a lot of debate over this, or these toxicity factors. This is the final slide I'll go through. So then with each one of these stages, based on the toxicity factors they presented and the metabolite mixtures they presented, we can calculate an action level for degraded TPH, or these HOPs compounds. This only looks at ingestion, doesn't take into account dermal contact. So very similar action level, say in stage 1, they're getting 420 micrograms per liter. We were estimating for degraded compounds for diesel 447. So it's pretty much the same number. So their studies concur with what we were seeing. how accurate are these? But as a default, we're going to assume that, again, degraded mixtures have the same toxicity as the parent compound mixtures. In this case, again, we're not, these action levels I show here, we're not taking into account dermal absorption, so they'd be a little bit lower if we did that. How accurate are the toxicity factors in CMO et al.? There's a lot of debate about that. And what would be the taste notice threshold for these metabolite mixtures? Chances are this stuff would probably taste and smell pretty bad, especially at higher concentrations. So that was another point here, is the non-degraded TPH hydrocarbons. Also, if you have undegraded TPH and such in BTEX, you would look at that separately. So that was one of the key questions that came up, is looking at degraded mixtures. There'll be a lot of debate going on about this for years, but at least we have a starting point now. That was the presentation. So thanks for joining in. I know we went on quite a bit longer than we did in the actual original presentation. I want to give some extra notes. So check the time tags associated with this to skip to individual sections. And as always, any comments or suggestions you have or updates or edits to our guidance would be much appreciated. Thanks.